we are going to be doing some math today. That's why I prepared the OneNote thing here, it's the first time I try, and I'm hoping, I think you can kind of like write some stuff fairly smoothly. Is the mic working? Yeah, it's working. Because I mean, I don't know. We'll see. We'll see if that will work out. Okay, so we'll see. Uh, it's quite cool. So actually, I can drag things around. Okay, nice. And I can probably just save that and just upload it to GitHub as well. So we'll see. What we're doing today. Cool. Yeah, I'll be using the browser better. Don't want. Um, what we're doing today is we're basically going to go and try to build a cubo out of the paper from. I'll almost say I think I'm going to pick. I think I'm going to actually pick the one from Multiverse Computing first, because computing portfolio optimization because that's my video. Because yeah, the only reason is I think it's a more comprehensive one, and so the Chicago Quantum one I think is a bit simpler. So I want to kind of go all in first, and then try to see if I can uh, towards prediction of financial crashes with D-Wave quantum computer. Interesting. That's what I want to read. The dynamic portfolio optimization. Read the full article. Oh, so they actually have done stuff with financial crashes. Interesting. I've downloaded it probably already, but here we go. So that's what we're gonna do. Is this recording? That's recording. Yeah. Okay, cool. So let's try to recap this a little bit, though. What we want to do is we want to build a cubo. Okay, so. And I'm gonna take multiple steps to do this because I really want to do it end to end. But then so the Lagrangian part here, I think it's gonna be just a bit more complicated because I've never done this before. But really, what this boils down to, okay? So what like if let's Google D-Wave cubo, okay? Example. What this boils down to is basically no. I wanted to see an example with the constraints where. Oh, that was actually not a bad example. I think I remember checking this one. There was a simpler example somewhere. There was a simple example that I checked recently. In their documentation, not examples. In the problem-solving handbook, reformulating a problem. Stating the problem. Close and accept. No. Reformulating the problem. Yeah, I think that's not it either. I found an example where it's like you basically all you need to do, right, is you need to find a way to encode your constraints into something that's a quadratic form, right? So it's almost, I can't find this example now. Maybe it was in the introduction. Cubo. Notation. Key terminology. Was it in the getting started? Oh Oh yeah, using good. I think this was these, yeah, with the TSP, with the traveling salesman. Yeah, exactly. That was actually illustrative enough, I think. So what we're saying here is this is the TSP problem, right? Like the traveling sales person, no, the traveling salesman problem. Um, and so what we're doing here is we're given like a set of cities and which are connected, and then you want to find the most optimal route or something like that. And so what we want is a function that is a minimum. So what we're doing is, of course, there's a constraint to this problem, which is that, like the traveling salesman cannot be in two cities at the same time. So how do you ensure that this is taken into consideration by the computer? Um, well, basically the configurations that have just one single one are true, right? Whereas the one where you've got like more than one, they are false. So you want a function that is at a minimum when this objective is true. So this is a way to express it, right? Like um, a plus b plus c equals 1, because yeah, like the answers that are true, basically if you add them up, they're just adding up to 1, right? So every other false combination has a higher result. So you can express it like these, and then the problem with this second expression above is that when a, b, and c are all zeros, we get a result of -1. Oh yeah, which is a lower energy than the true states, and the traveling salesman has to be in at least one city, right? So that's also not a good solution. Mm. And so the solution is to square the original question. So if you square these, then you're getting a 1. Okay, then you're getting a 1, which is actually higher energy than like when it's in one place, right? Yeah. So that's your cost function. And if you expand these, you get this thing here. So in this has the shape of an actual cubo, because it's got like linear terms that are just like, so you've got a constant term, you've got like linear terms, and you've got like the quadratic terms, which are basically sort of the correlations between the variables. So a times b, a times c, and b times c. And so now if you take a look at these, you see that all the true states are the ones that have the lowest energy. And so that's your cubo. Okay. You can also convert a cube into a graph where the variables are the nodes, and the nodes have the linear terms associated to them, and then the edges in between the nodes are the quadratic terms. I think that just should be the front page of the wave. That's really all you need to understand these. So what we're trying to do is we're trying to do something more complicated, obviously, which is we're trying to express something like these in cubo form, or we're trying to figure out whether this is expressible in cubo form, right? And so here our variables are the qubits, which they represent basically the assets, but not only these, it's the assets like, yeah, just maybe one more note. So what you want to, one way to express this here, based on what I currently understand, right, is that you have a matrix, right? So you have a matrix where the diagonal terms are the linear terms, right? So you'd say minus 1, minus 1, minus 1. Like this is your like A, B, and C, right? And then the so this would be A times B, and this would be A times C, and this would be B times C. right? Right. So these are all the possible combinations, and so we don't care about this other part of the matrix, and so that's another way to express it for D wave. Is like you just fill this out with numbers, so that would be literally like 2, 2, and 2, right? I don't know what you're gonna do with sort of the fixed terms. Maybe you just add them at the end. I don't know where would you put that though. Um, but that's what you would give. That's what you would give to the D-wave system. Um, yeah. Cool. So we are now gonna try to do something complicated. So what we want to do is we want to do. Well, we want to turn these Hamiltonian here, right, into a cubo form. Now, the variables here is like this is WT. So WT is basically, if I remember this well, let's see. So it's explanation of profit. Because here there's also a version with the there's also a version with the fees of changing, which maybe we should just go ahead and do this with this one. I think that's cooler. It's more complicated though, but we should just go ahead and do this with the equation 12. So it's equation 12. Um, we're not going to do the continuous case because I haven't read this yet. But that's the point, right? Like that's the whole thing here. So you have WNT, and so this is the vector of your assets. And this X is basically your qubit, right? Like that's a qubit, and this qubit is so we have like 3 sub indices in here, N, T, and Q. In terms of what is NQ though? Like I think I missed that. What is NQ defined? Or what does the Q mean at all? Is it from the continuous? No, that wouldn't make sense. Anyway, no, it's too low already. This is where we are. So what this is saying is that our vector of assets, right? And maybe we should just, for the sake of like the handwritten example, we can just have like maybe just 2 assets, like 2 assets, and then I don't know, like 2 steps. Like, because T is basically I would say 2, like, so we have 2 steps, right? 2 investment steps. Because remember, what we're trying to do here is that we're trying to kind of come up with the optimal investment strategy, which like for the next T steps. So this means not just like what's the next best thing to do, but like how should I invest in the next 2 steps, right? Like assuming that in each step you can change your portfolio, so you can kind of change the way you're investing. Um, I'm really having a hard time because I don't wanna think too much about whether or why certain components are in here in the equations. I probably want to reason these at the end. I just want to go through and actually try to deduce and try to build a cube out of these first. Just brute force through this exercise. It's 2 to the power of q. Why 2 to the power of q? What is this? So q is, they say here q is the where was that written? In terms of NQ beats, a binary encoding of each variable. Okay, so I shouldn't care about these, should I? The binary encoding of each variable. For this, we choose a binary encoding of each variable w and t in terms of nq beats. Ah, no. Oh, okay. Wait a second. Of nq beats. There are several options for this encoding as discussed in reference 11. For simplicity in the paper, we choose to work with the binary encoding. What is Q though? It's maybe the amount of assets. Discrete asset allocation. An industry rebalancing is done in discrete time steps t, and it is common for funds to trade assets in large discrete packages. In this setting, the problem is naturally recast. For this, we choose binary encoding for each variable. So we've got different variables w and t, right? Like, and what I assume is like w and t is basically a sort of a vector of like, you know, you've got like your asset 0 at time t, you've got like asset 1 at time t, you've got like asset 2 at time t, etc. Right? Like we said, we have just, let's say, 2 assets, okay? 2 assets to choose from. Or we'll just make maybe 3 assets, okay? 3 assets. So that's what we have. Right? And then we have 2 times, so this is t0. So we have w n, like what is n? T1, and so this is basically T0, T0, T0. So you kind of have A0 at T1, A1 at T1, A2 at T1. That's what we have. What is N though? What is N? What is N? By construction, we have that the maximum investment per asset is 2 to the power of nq minus 1, which is naturally encoded in the formalism. Investments also in packages of 1. Oh, okay, I get it. So, ah, so this is this is basically telling you, oh, this is for asset n maybe. So what this is telling you is telling you that that's not these, that's not how it works. So this is basically the sum of how much you want to invest, how many packages you want to invest. So you're saying, for example, like, okay, so Q0, right, would mean like, because we go from Q0, so it would mean like 2 to the power of 0, which is 1, and then like asset, what is n? I don't know, T0, 0, right? So this would be for Q0. But if we just, let me just get rid of these. So what this unfolds into is like 2 to the power of 1, a n t0, 1, and now we'll get 2 to the power of 2. So we're doing an example, okay? We're doing an example. A n, well, that should call it x maybe, but okay, I'll just keep it as a. T0, 2, and this is divided by k because we want to normalize these. And okay, so this is, so I think that's one asset. I think that sub n is, it's just one asset. So this means n is the asset number, the asset number. So what we're saying is here is, do we want to invest, like, and that's just a variable, right? That's your, those things are just the actual qubits. So it's like, that's one, that's two, and that's four. So 4 plus 2, it's 6. This one is 7. So the maximum you can invest is k prima, which is 2 to the power of nq, which is 3, which is 8 minus 1, so it makes sense. So k prima in this case is 7 for us, which I just proved. So I think I got it right. I think that is basically, so what you're saying is this is kind of like asset, say 0, right? For n equals 0, and that's just one variable, right? So this means for each asset in this setup, for an asset 0 at t0, we actually have 3 qubits. Yeah, so we have basically 3 qubits. Now, this is because the maximum amount we can invest is 7. So this means that the more we want to invest, the more qubits we need per asset. Nice. Okay, like it. That's key, because I hadn't really gone through these yesterday carefully enough, I think. And then, yeah, the size of this is going to explode, right? Like, and they did it for like 50 assets or something. That's just nuts. We'll do it programmatically, okay? So we'll actually write a bit of code, maybe, hopefully today as well. We'll see. Okay. So now I understand these. And so the number of total qubits are needed are the amount of assets. So it's n times nt times nq. So nt basically means we want to have, so we have, what do we say, 3 assets, right? So I have 3 assets times 2 steps, right? Times times 3. nq is 3. Is it nq 3? I think so, is it? Yeah, because, no, 4, 0. Yeah, no, nq is 3. Okay, yeah, that's correct. So it's like, okay, cool. That's like 18, right? So we need 18 qubits for these. Okay, cool. Equals the peak variables. Finding the optimum before it weights at a given time is if we're going to find the ground state of the minimum over the variables. Blah blah blah. So okay. So now what we need to do is we need to build a QBO based on these. How do we do these? So I guess it's we need to replace these. We need to replace these, right? Which maybe I should start. So let's have it as a reference. We have 1 divided by k, and then we have like the sum of these, right? And then let's use NTQ. So we have these, and this is basically WNT. So remember, N is the number of the asset. So we have two assets. So what we need is we need to understand like so what we need is a collection of we need like I said 3 assets, right? Like so we need these, and then we need these. So 0 1 1 1 2 1. So we have 6 variables like these. That's what we need to find out. And so we're gonna have 6 of these, and we're gonna go, and now I think what we have to do is we have to replace these. I'm scrolling with a pen in here. Okay, so W sub t appears, and that's a sum over t's. It's a sum over the times, and then I'm assuming those are vectors, right? So this means what we have is this is kind of one vector, and this is another vector. So we have these repeated twice, because that's the vector for t0, that's the vector for t1. So the whole thing repeated twice. And so what we have is, well, mu or mu sub t is this was the was it the earnings or something like that, like the return? Yeah, that was the return. This was the whole risk thing. What was that again? That was the risk. Transaction cost. I haven't gone through transaction costs yet, but let's do bit by bit. Okay, so this is the actual variance of the portfolio. Return at time t. What is this sum symbol in here though? Is it again the expectation value or something? Or is it the... Let's start from the easy one. Let's start from the easy one. So, which is the first part. So there's kind of this kind of like the part that's like this mu sub t transposed, and then I guess that's wt, right? Like, yeah, using the same w seems to be confusing. So that will be v0, and then we're going to have another component to it. So that's for t0, right? And then we have mu1 transposed times v1. So this is basically these. Is the transposed of a vector is just the sort of, if it's horizontal, it's the vertical version, right? Transpose vector. Transpose of a vector. Row and column vectors, I think that's the only thing, that's the only difference. So a column vector, blah, blah, blah. A row vector is these. Okay, so basically the transposed of these is just like the vertical version of it. Okay, that was correct. That was correct. Yeah, because you're gonna have the return that's also a vector, right? So these are the returns of each portfolio at time or the expected returns. But how are the expected returns calculated? How am I going to calculate these? Is it based on the history? I guess. But like, you'd still have to make, so you'd still have to calculate them somehow. So you have to pick a model or something, right? Um, oh, wait a second. So here they actually define this some t thing. This, what is the name of this symbol? It's an n by n matrix. But what is this? Forecast returns at time. So we also define mu sub t, the asset's forecast returns at time t. Okay, so yeah, we need to calculate what are the forecasted returns of that asset at time t. And this is the asset's covariance at time t. Okay. Yeah, so but those are things that need to be predicted, right? So we need to. Okay, but this we need later. So this is the return. So we didn't know that. We'll need to calculate that. So we'll just probably make up the numbers first. But I guess they use some. Yeah, I guess they must use some model for these. So this means, yeah, well, those pretty much look like they're going to be linear terms, right? Because in here you just have these W's, right? Like this W00, 10, 20, which is basically these thing here. That's a constant. So you're kind of going to have, basically what you're going to have is, I mean, let's unpack these, okay? Let's call, I guess what this is going to have is going to have like a mu 0 for asset 0 is going to have like a mu 0 because we're at t0, right? So for asset 1 and a mu 0 for asset 2. So these are the expected returns, and then that guy here is going to have like a mu sub 1 0, mu sub 1 1, and mu sub 1 2. So we'll have to calculate those because we don't know what the values are based on real data, and they just both, kind of in column form, they multiply with the row version of these, and so you basically actually have well, I guess what you have is, I mean, you have these metrics, right? So you have these multiplications, so 0 1 0 2, so these times these, right? My handwriting is awful. So I guess what you have, yeah, well, it's just each term kind of multiplied by the corresponding one. Yeah, so you just basically have like mu sub 0 0 times w 0 0 plus mu 0 1 times w 0 1. It's awful handwriting. 0 2 times w 0 2. Yeah, 0 2. Sorry. So this is what these unpacks into. Of course, like all minus, right? All minus. And so, okay, cool. And so what we're gonna have is then we're gonna have the same repeated by this term in here. I mean, I'm not gonna go all the what is going on here? What is going on? Sorry, this just turned nuts. I guess my pen. What the hell? Sorry. Where was I? Calm down. It's all good. I was here. But you kind of see, and then each of these elements And then each of these elements, right, will unpack into what we had calculated before, which is kind of, what you have in here, right? These. So you would kind of have like, um, a so you have this minus, 0, 0 will be kind of all multiplied by like 2 to the power 0 times, what was that? So yeah, basically exactly these guys. Yeah, we can just already divide this by k, doesn't matter. And so 2 to the power 0, and then this is the actual qubit of of time 0, acid 0, and q 0, and then you're going to have like 2 to the power of 1, and you're going to have like 0, 0, 1, and then you're going to have 2 to the power of 2, x 6, 0, 2, something like this, right? And that's what you're going to have, exactly. So these terms is going to be a linear term for each of these qubits. Okay. But how are we going to lay out these qubits in a matrix? That is a good question. This is the awfulest handwriting ever. But I get so, but okay, but what I'm saying is this doesn't seem so complicated. I mean, what is okay? So we should be able to easily compute that, like with Python, and making up these numbers. But like, what are the two dimensions of? I mean, yeah, okay. So each of these terms. So what we're gonna get is like we're gonna get a matrix of like 8 by 8, right? Because if we have 8 qubits, 18. Oh, 18 by 18. Oh god, what's that? Calc. Rechner in German. German laptop. 18 times 18. Oh, 324 elements. Okay, cool. So that's what we're going to have to do. I mean, we might as well just start building that. Why not? Maybe it's better than just using handwritten notes. But okay, but that's one term. So this is the first term here. This guy. Here, it's kind of the same. That's also going to lead to linear terms. And so we will have to then add those things. So let's kind of go back for a second, see what that weird like sign meant. So each of these components, blah, blah, blah. And this is the assets covariance at time t. The assets covariance with the market, I guess. Covariance with the market. So it's the covariance with the market, I'm assuming. But why we do it this way? So okay, so let's kind of open another. So we're now going to take a look at these WT. This is T and WT, so WT transpose. So why are we doing it this way? Uh-huh. Okay, I guess what this means is, yeah, you've got the covariance with the market, and so you are trying to achieve the same than here, but like instead of the returns, you want to have the covariance. So what you have to do is and that essentially means like you surround it with these. Like the only reason you surround it with these, you sandwich it with these, is just because you want to get it in the form of a sum. Like each WT was one of these V's here, right? So so basically what you're gonna get is you're gonna have like so what this is gonna unpack to is like you're gonna have like 0, 0, 0, 1, and 0, 2, right? That was whatever. 2 zeros, that was maybe 1, 0. So you're gonna have these times you kind of have basically now the yeah, okay, so that's the way this will multiply, because I'm assuming this is a constant. Is the assets variance at time t. So this is just a constant per each asset. So what you're gonna have here is like you're gonna have, I don't know, I don't know how to even write it, but like that would be, it would be like covariance of 0, 0 times 0, 0 plus covariance of 1, 0 plus 1, 0, etc. Right? So what you're gonna end up the same is just like, yeah, so that term multiplies with this term, right? Um, mm, and I mean, as W, well, wait a second. Does it work like these? So the V0 would be, yeah, each of these components, right? So what we're saying is we're doing these times these, right? And so you're getting these. And so we had then these packs into that. So let's unpack it until the end as well to see what happens. So you actually have, so you actually have here, like, I want to know, is this a linear term or is it a quadratic term? It should be a linear term times the covariance, which is a constant, that's squared now. So what you have is covariance is a constant, and then that thing squared is basically, yeah, well, it's your, so what you end up with having here is, again, it's like the k, so you have like the k here, and then you have like these, 0, 0, 0, then you have these like 0, 0, 1, and then you have these. Am I doing something wrong in here? And that is squared, so it's basically this squared and this squared, so kind of this goes away here squared, and so then you have these here. So this is actually giving us some quadratic terms. Okay. Yeah, some quadratic terms, I guess. But because what you have is you basically have like these plus 2 times these. That's like 4 times these. Multiplied by itself. Where am I? Right? So you can have, again, handwriting is not my thing. Oh. So you do sort of the the distribution kind of thing. So you can have like squared, and then you have like 2 times these times these, etc. Right? So we actually have. So you actually have. some quadratic terms in here. I guess that's a linear term, right? Because that's just kind of the thing with itself. Okay, I didn't expect that. But am I doing... Is this correct? Like, that feels a bit too complicated, to be honest. It's basically, I mean, it's just a covariance. It's the covariance with the market. But I guess because you're going to have 3 qubits that are going to be used to represent the amount of investment that you want to actually have, right? That's actually, yeah, those must be correlated because what's the covariance? It's like, not the covariance. What am I saying? What I'm saying is that it's basically what will be the rationale behind this? Like, because here you want to multiply the expected return of each asset, but here what you want to have is the but why don't you also why don't you just take the covariance of each asset? Why don't you just take the covariance of each asset with the market and transpose it? Wouldn't you get this? Wouldn't you get something then similar to the first term? So just it's the assets covariance at time t. Oh wait, it's not a constant, it's a matrix. So mu t sub t is an n-length vector, while the covariance is an n by n matrix. N being the number of assets. No. Yeah, number of assets. Ah, it's the assets covariance, like the covariance of all the assets with themselves. Ah, I get it. So that's not... Okay, so I'll trash this. Can I trash this? That's not true. That's all false. So what this is I get it. So you have okay, so we have this. Let's do the case of V0, right? Which is the W0 here. So, and we're trying to do this kind of like, so this is the vector W0. W, what did I say? 1, 0, 2, 0, transposed times, and now you have a matrix, right? And then you have the assets covariance. I'll call it like cov 0, 0, cov 0, 1, 1, cov 2, 2, right? And so this is a covariance of each asset with itself, which should kind of be 1 because they are. It's 1 or 0. I don't know what's the definition, but anyway, this should be covariance of 0, 1 and covariance of 0, 2, and this should be covariance of 1, 2, and this should be covariance of 1, 0, and this should be, yeah, covariance of 2, 0, covariance of 2, 1, exactly. And then you have again like the, so your V0, which is this one, yeah, V0. So this is transposed, so what you actually have, let's make use of this beautiful drag and drop functionality here, is, well, you have the 0, 0, 1, 0, 2, 0, so you have these times these, and then this is actually 0, 0, 1, 0, 2, 0. So what you have is, what you're doing is you're multiplying this element, so you're multiplying like, what would the first row be? Would be like W00 times cos 00 plus W, no, what are you doing? How do you multiply? So the other way around, it's like these with all these times these. That's what you do, I think, right? So you do like W00 times cos 00 plus W00 times cos 10 plus W00 times cos covariant 20, and all these times 00. So they all, yeah, okay, so they're all squared, which is basically, yeah, but it's basically also leading to, it's also leading to quadratic terms, isn't it? Why? Is the variance of the portfolio return at time t. It's also leading to quadratic terms because each of these will now unpack into basically saying covariance is 0, 0. Yeah, okay, actually, you can factor these covariances. No, you cannot factor. No, you can factor these out. So you basically have the covariances added up times, and now you have this W00 squared, which is basically, you know, your give it. And the k squared can go here, and that stays square. That stays squared. And this is where we're going to have then quadratic terms. So you're actually going to have quadratic terms. Does this make sense? Why it makes sense? Tell me why it makes sense. Because it makes sense because those beats are used to define the investment amount. Why this didn't show up here? Like, because you just have these transposed, and so it's just you're just adding stuff. The problem is here we're multiplying something by itself. Yeah, well, I guess that's what happens. It's variance, right? So that's the variance of the portfolio, and the variance has its quadratic terms. I think that's it. I don't know. Maybe there's just no intuitive explanation for that. But like, what was the formula of the variance again? Maybe that's just, yeah. Well, so this involves a square. Is defined as the sum of the square distances of each term in the distribution from the mean. What is the intuition behind, like, y is variance squared? It's convenient. The variance is a way station on the path to standard deviation. The variance is a squared value because it's convenient. The variance is a way station on the path to standard deviation. What does it mean? Why do we square? Why do we square in variance? Exactly. The arithmetic mean of the square differences between each value and the mean value. Squaring makes each term positive. Yeah, that's why. Okay. Okay. So you don't cancel out items that are below the mean. So that's the reason. And that leads to quadratic terms in here, in our case. So this is going to have, that was a surprise. That was a surprise. Okay, so this is going to have quadratic terms. So, where am I? So, okay, so it's going to have quadratic terms because we're squaring these, right? So the quadratic terms are going to be like, so I guess if we square these, that's just not really a quadratic term because it's with itself. So I think that's just a linear term. But then we're going to have 2 times these, and we're going to have 4 times these. Then we're going to have another 2 times these. So we're going to have 2 times these, because I'm going to assume that's linear because it would be just squared of the same beat. And then we're going to have like 4 times 2 times, so those are the terms. And then we're going to have also 4 times these, which is kind of the same like here. We're going to have 4 times. There's probably a formula for these that I forgot. 2 times, I'm just doing the distributive product or something like that. I don't know what it's called. These, and then we're going to have basically 4 times 4. Oh yeah, that's 2 times 2 actually. 4 times 4. Yeah, we're going to have these. So some of these terms add up, so those terms add up. This is 4, and these add up, so it's an 8. But like, that's roughly for one asset. So I'm starting to think about like how we're going to build that programmatically, and what we're probably going to have to do is we're going to probably have to build a matrix. I think we can turn these into, like, we can read these as actual binary numbers and use them as indices for the matrix. And then how can we, yeah, and then we're just going to go almost manually, I would say. No, how to programmatically build that, or in a way that I don't have to do the full expansion. Yeah, but that's basically sort of a cat through this term. Yeah, I'm like sure, like I have to add here this whatever symbol disease, right? And this k squared in here, and the covariances matrix goes in here. Okay, cool. So we're left with one part. No, we're left with two parts. If we really want to take the transaction fees in, we're gonna go all in. So then there's still this component here, and then these parts. So this, we know this is done with we know that this comes from the Lagrange thingy, and I don't know how we're gonna calculate that though. So how do you factor in the transaction costs? The problem stated above is simplistic as it does not account for transaction costs. These frequently are comparable to the profit incurred by a given portfolio. The transaction costs are typically a percentage of the transaction, whether buying or selling assets. They can be expressed in terms of unnormalized weights, so it's a cost. With VNT, the cost percentage, for example, 0.001 for 10 basis points, meaning a cost of 0.1% of the total amount of the transaction. The objective function, which counts for these costs in terms of normalized weights, is given by these. Okay, so you're just adding it as a penalty. Note that this is not the form in equation 6, since the delta of WT correlates times t and t plus 1. Oh, okay. Yeah, that's going to be complicated. So the percentual transaction costs are not polynomial in the variables W and T because of the absolute value function. This could limit the applicability of some quantum optimization methods. To get around this problem, we can tailor expand the absolute value in a way similar to the expansion in reference 7 for a step function. Alternatively, we could introduce ancillary QVs to treat the problem exactly as explained in section 6. Here we choose to approximate equation 9 by a parabola in the considered range. What? This is an excellent approximation to equation 9 when the W and T are discrete variables and k prime divided by k is small. The cost function therefore reduces to these, with lambda the optimal parabolic coefficient for the transaction costs as discussed above. How the hell I'm going to calculate these? Finally, let us remark that in this setting, the percentual profits of the trading trajectory are given by the expression profit equals. Okay, yeah. The percentual return minus the percentual cost. So delta WT correlates times t and t plus 1. So that's a whole new game here. So we're going to have a constant here that we didn't know how to find, which is this VT. Sorry, this lambda, which is, they say, the optimal parabolic coefficient. What is the parabolic coefficient? Optimal parabolic coefficient. Is this a thing? So this is some... Bam, I've opened a can of worms. So let's read that again. I intuitively, I think I get it. So what they do is there's VT, which is basically a not normalized percentage of, like it's a cost. It's a cost that relates the investment at time t with time t plus 1. Fortunately, because we pick in our example just two t's, and we're going to have just to do these ones. So it's going to have three. So what we're going to have is we're going to have like, you know, we're just going to have the coefficient for like asset 0, and then we're going to have like between like v0 or v1 minus v0, whatever that means. Yeah, that's the investment difference, right? Like, of course, that makes sense because that's the investment difference. It's like if you know you have like v0 is like w01, w11, w21, right? Assets 0 to 2 at time 1 at time 0. And this is then v1 is these. So it's basically the same, but at t1. So what you want to do is you want to calculate what's your change in investment, right? So if v0 is like, and I'm gonna talk, maybe I'm just gonna like talk percentages here, right? But if you want to have, I don't know, 0.5% here plus 0 here plus 0.5% here, and now your change and now your changing strategy in v1 is that you want like 0.3300 and you want 0.3300 and you want 0.33, sorry, 10 0 0 1 1 1 2 1. So you want the difference between these two vectors. So what you're basically getting is yeah, so you're gonna get a negative because you're doing v1. So what are you gonna get? Calc. Yes, I have to calculate. I have to use the calculator for that. So you're gonna get like 0.33. Germans use a comma. So we're gonna get minus 17. So we're gonna get is like that difference will really be like minus 0.1700 plus 0.33 these, and then minus 0.17. Well. No, wait a second. That's not entirely true, because that's not like, those are two different variables, right? Those are two different variables. Yeah, okay, so no, you're gonna get like, so that's not true. So you're gonna get like 0.3301 minus 0.500. You actually, you're not gonna get like these, right? Like you're gonna get these because when you're expressing, and that's nice because you're expressing with a minus, is like that's gonna play positively towards your minimization goal, because what you want to do at the end is the Hamiltonian, kind of find the minimum value. But here, because you're adding these and you're minusing that, like and that's going to all be multiplied by this constant. So this constant is going to play like the overall is like, you know, that's going to play positive for you in this case, it's going to play negative for you in this case. Okay. But it's the change, that makes sense. It's the change in the portfolio, it's the change in investment what you're calculating. It's the change in investment what you're calculating. Now, how do you find, the biggest challenge here is going to be to find this lambda. But what I like about this is that it just seems to be adding linear terms to the matrix. You're not going to get quadratic terms here. So it all seems linear. Okay. And now the last part. Yeah, I mean, I'm not going to get this into code, I think, with the time that I have, I think. Okay, but what's the last part? So now we understand the code, so we understand the I mean, still how to calculate lambda, that's going to be, yeah, sorry, let's not close, through that, over that, or whatever the expression is. Transaction costs. So what they're saying here is that, so this would be the non-normalized way of doing things. The percentual transaction. Yeah, but that's not. No, something's wrong here. So this should correlate. This should correlate somehow. Like, I think this should correlate those two. It should actually correlate. So you should actually have a term like these. Maybe that's just the way it is, like these. That's how you do it. I don't know. That seems more intuitive, right? Because you want this particular combination to have this overall effect. It should correlate times t and t plus 1. Not so sure which is the correct one. Like, if you know, mathematically speaking, it seems like the first one should be the correct one because, well, you're just doing, you're just subtracting one vector from another, right? It's the delta, so you're just doing, you know, what's the delta, right? You're just doing v1 minus v0, the change in investment, and multiplying that by this lambda. Yeah, but there's an absolute value here. Why? Oh, okay, wait a second. So these minus these in absolute value. It's the sum of the times. So I didn't take a look at equation 9 carefully. It's the it's the sum of sums. So it's the sum of times. No, you start with these ones. So you start with asset 1, and then you, of course, do this by time plus 1. So yeah, so basically you're getting v1 minus v0 times like this thing for asset 1 or asset 0 times 0, right? It's the cost percentage basis points. That's of course not normalized. The objective function which accounts for these cost in terms of normalized weights is given by these, where correlates times t and t plus 1. The percentual transaction costs are not polynomial in the variables in t because the absolute value because of the absolute value function. Also, they're saying that the absolute value function. Why is absolute value? Like that makes no sense. Like I would assume that maybe the minus is carried by that coefficient already, right? What am I saying? No. That's stupid. It's always a cost. So it must always be plus. Like changing your investment strategy, it's always a cost because you've got to pay the fee. So it's always going to be plus. So this is all nonsense. Nonsense. It's always a cost. It's always going to be plus. So you need to have the absolute value. No, copy what? But I'm still like, it's a minus, right? So how would you? Unless it correlates at the qubit level, right? No, it does not. It's a minus. How would it correlate then, the two things? This could limit the applicability. So the percentual transaction costs are not polynomial in the variables w and t because of the absolute value function. This could limit the applicability of some quantum optimization methods. I don't know why. To get around this problem, we can Taylor expand the absolute value in a similar way to the expansion in reference 7 for a step function. Alternatively, we could introduce ancillary qubits to treat this problem exactly as explained in section 6. Here we choose the approximate equation 9 by a parabola in the considered range. Okay, so here's why. The approximation, okay, so that's like so how do you calculate this function? That's the question. So how do you calculate this function? This delta function. With whatever the name is the best matrix of transaction costs at time t. Okay, so that's the matrix of transaction costs. Yeah, we're gonna do this. Okay, so I really want to do this with the transaction costs. So you have this matrix. Like, let's get rid of these. This is all wrong. Can I select all of it? Yeah. This is all wrong. So so we have this thing, and this is a matrix. This is a cost matrix. Transaction cost matrix. The best matrix of transaction costs at time t that is compatible and realistic with market conditions. Okay, but what are the elements of this matrix? Is it just a diagonal matrix, or and so W and T are values between 0 and like k prima divided by k. Forgot what k prima was. So that's roughly these. And then the cost function is the optimal parabolic coefficient of the transaction costs. What is the optimal parabolic coefficient? What is these? Optimal control of the convective velocity? No. The parabolic coefficient. What is the parabolic coefficient? Parabolic coefficient. So a positive quadratic coefficient causes the ends of the parabola to point upwards, a negative to point downwards. The greater the quadratic coefficient, the narrower the parabola, the lesser the wider the parabola. Okay. And what? Oh, it's squared. Uh-huh. So that's why you end up with the correlations. Why do we square it though? So the matrix costs are in here. Well, that's gonna be damn tricky. It's really gonna be tricky. The best matrix of transaction costs at time t that is compatible and realistic with market conditions. So that's an actual matrix of transaction costs. But I'm not so sure what the shape of these metrics is. Like, is it diagonal? Is it not diagonal? What are the off-diagonal terms then? Meaning, and here you're gonna have like, I guess the delta WT is kind of what we said, right? So that is really like W, like, you know, so that's really like V1 minus V2, right? And that's what you're gonna have in here. And so, yeah, that's gonna be basically, you're gonna have like these, you know, 0, 0 minus 1, 0, and you're gonna have like the other way around. 1 minus 0, 0. You're gonna have like 1, 1 minus. My brain is about to fry right now. What am I doing? So I already don't know what is T, what is not T, but you know what I mean, right? So you're gonna have these, and you're also gonna have, of course, you have to have the transpose version of it, which is just the column version of it, right? So you have like etc. And so these terms are going to be basically they're going to end up being like multiplied by each other, right? Because here we have this matrix of cost, which I don't know what it is, but you're going to end up having like the sum of these Like like in a similar fashion, we end up here with these, right? Like with the covariances. So you're gonna end up with something similar like that. So this is gonna really also correlate the qubits. This is also gonna correlate the qubits at that level. Yeah. Yeah. And that's gonna kind of like I like how this really like has this interleaving effect, right? Like at the qubit level, because you're using more than one qubit to represent the amount of investment. Like that is so much more powerful than what the Chicago quantum guys are using, because they're just using a qubit, like they're just using a qubit to kind of as a binary, like I invest or I don't invest. Like that model, like that qubit is so much more powerful. But like how very powerful, like detailed, right? But how am I going to build that programmatically? I don't know. And that's probably going to be the next video. I'm going to try to sketch something out, okay, before I start this video. So I wanted to go through all the terms, but we understand these. So that's kind of roughly the way it's going to look like. I better not lose these notes. Okay, so now we're left with one term. Oh, well, I don't know why we square it, though. Why do we square it? So, well, first of all, we're approximating it. Why are we squaring it? Can someone tell me why are we squaring it? Is it because of these transpose? No, that's not the... It's got to do something. It's got to do with something related to these. Like, I don't understand why you approximate it with something that needs a parabolic coefficient. Like, for the transaction costs. What is the parabolic coefficient of a matrix? Like, parabolic coefficient of a matrix. Does this exist? Oh, because actually, oh, okay. So there is a way to represent a parabola in a matrix form. Okay, so let's go through these. Continue the epic quest on finding matrix representations from here. With the last part, the only conic section left, the parabola. I will present one idea of how to structure this representation, but I hope to get the examples of more elegant representations. The objective is to find a matrix representation for a generating element, such as the coordinates of a parabola are directly readable from some of the elements of a matrix power. Remember, addition can be presented as the block MA+. I don't know what this means. Then observe that all... If we take a look at this new matrix, now the lower right 2 by 2 block will produce n at position 3, 2 if the matrix is raised to the n. What remains is to linearly combine these. We therefore create one last row, and there was a place the coefficients for our second degree polynomial. So that's your parabola. Our polynomial value will now end up What is these? I don't know if that's the thing, but it seems like that is a coefficient. But I don't know why we square that. I really don't know why we square that. But it's got to do with this approximation, okay? So this is maybe I'll ask the authors, why do we square that? I mean, to get on this problem, we can Taylor expand the absolute value. Okay, so the reason maybe I should check the reference 7. So the percentual transaction costs are not polynomial in the variables. What does this mean, that this is not polynomial? So they are not polynomial in the variables w and t because of the absolute value function. In the variables w and t. What is what is a not a polynomial function example? Okay. Because of negative exponents, because of fraction exponents, or because of some sort of division. So that's non-polynomial. It's non-polynomial because of the absolute value function. Okay. So the fact that it's absolute, that it's got an absolute value function, it means that it cannot be polynomial, and that is a problem. Oh, so maybe we square it to avoid these. I get it. Maybe we square these. So we're squaring these just to avoid the okay, so we're squaring these just to avoid using the absolute value function. We need to use the absolute value function because why? Yeah, because we're interested in the difference, but like the absolute difference, right? I'm not so sure why something that's got like the absolute value cannot be polynomial, but I guess that maybe it's something that I just like. Yeah, I'm assuming it's true. I'm assuming. Let's assume that's the reason, right? Maybe I'll just Google that. So function. Polynomials are expressions which only consist of variables and coefficients, using only the operations of addition, subtraction, multiplication, and natural exponents of variables. The absolute value operation is therefore not included in the scope of polynomials. Okay, cool. I'm happy with that. I guess I could dig into these, but like, man, I'm learning things. I'm learning so many things. That's cool. Okay, so it's not polynomial. This means if it's not polynomial, it means that it cannot be a Q into QO. That's good. That's good. That's good. That's good. In order to avoid these, we need to approximate that. So we need to do this Taylor expansion, which I have no idea what a Taylor expansion is. I've read this many times, but I have no idea what it is. What is a Taylor expansion? So a Taylor expansion, Taylor series, Taylor's theorem. Let's go learn something new. In mathematics, a Taylor series of a function is an infinite sum of terms that are expressed in terms of the function's derivatives at a single point. For most common functions, the function of the sum of its Taylor series are equal. For most common functions, the function and the sum of its Taylor series are equal near this point. Taylor series are named after Brooke Taylor, who introduced them in 1700. If 0 is the point where the derivatives are considered, the Taylor series is called a Maclaurin series. So the partial sum formed by the n first terms of a Taylor series is a polynomial of degree n that is called the nth Taylor polynomial of the function. Okay, so this is basically a way to approximate functions, I guess. Right? As the degree of the Taylor polynomial arises, it approaches the correct function. This image shows the function sinus x and its Taylor approximations. Okay, so this is the orange is 1, then the green, the first is the red. It's just these. Then the orange is these, then comes the yellow, then comes the green, then comes the blue, then comes the purple. Okay, interesting. It's an infinite sum of terms that are expressed in terms of the function's derivatives. So it's the integral of the different derivatives. Okay. Taylor series for real or complex value functions that is infinitely differentiable at a real complex number. A is the power of series. Okay, so this is third derivative. Examples. Let's say example. So the Taylor series of a polynomial is the polynomial itself. The Maclaurin series for this is blah blah. And let's do, I don't know. The Taylor series for the natural logarithm x at an arbitrary non-zero point a is this. Okay, so you're doing the first derivative, the second derivative, blah blah blah. So it's a way to express. Okay, so we should probably, the gist of this is you should just we Taylor express the absolute value in a way. Okay, but that's actually how do you Taylor expand the absolute value? And that's probably what reference 7 is saying. We should probably go and take a look at reference 7. Stack exchange. So reference 7. So this is oh, it's I think the same authors. Oh no. Oh, forecasting financial crashes using quantum computing. I think that was the other. Let's unload these. So here there's something they've. Oh, come on. Come on. I think there's another way to get there, you know? There's another way to get there. It's probably this one. Oh, wait a second. I think it's this one. Yeah. Let's try Taylor. There's no Taylor. Absolute value. There's no absolute value. That's not this. That's not this. But I think I'm on the right track. So basically, it's the Taylor expansion of the absolute value, what we're looking for. And so that's not what I'm looking for. Taylor series of absolute value. Taylor expansion of absolute value. Is it here? Taylor. No. Okay, but it's like that. So that should be easy to approximate, actually. Well, that's actually this. Where is it? No. Well, by squaring it, you're almost approximating it, right? Because by squaring, you're making a parabola. So you're actually, by squaring, you're doing something like that looks like that, right? And so it's almost these, to be honest. Okay, I get it. Yeah, I like it. Mm. How are you gonna introduce auxiliary qubits to treat this problem exactly? I have no idea. That's out of scope for me right now. Um, okay, but there's a parabola. Okay, so so we're approximating we're approximating the absolute value with a parabola in a range. Ah, and that is the range. Okay. But how do they find lambda? The cost function here is, so with lambda, the optimal parabolic coefficient for the transaction costs. Okay, now I understand why it's squared, but we don't know how to find lambda, the optimal parabolic coefficient for the transaction cost. So we have to find a parabolic coefficient. Yeah, well, the transaction costs, this is a matrix. Transaction costs. I think I gotta. So the transaction cost is a matrix, and the transaction costs are a matrix. Why? Why are... Okay, that still was not completely clear to me. Why is this approximated as a matrix? But okay, roughly, we can come back to this as we build that part. But I understand why it's square, because we're approximating the absolute value, and this alpha is this lambda is somewhat related to the transaction cost. And I think the last part is kind of, I think that's going to be the trickiest, but I think I know what they mean here. Where not exactly. I don't know how they construct U though. Why is this not showing? That's showing now. So what happened? Oh, okay. There's just too many sections now. Section 5. So, okay, in profit, but then finally let us remark that in this setting, the percentual profits of the trading trajectory are given by the expression of these. The percentual returns minus the percentual costs. The profit, yeah. Okay, but now, how do we get the last part, right? So this is the tricky. So the last part is to basically ensure these constraint, and this is where the D-Wave page at the beginning plays the role, right? So we want to have the constraint that we don't invest more than K. The goal of the modern portfolio theory is to find a trajectory which maximizes returns for fixed risk. It is common to request the total investment at any given time is fixed. Okay. Oh, so actually this means... So this is crazy. So this actually considers that... And okay, it's the same. So we're considering a fixed investment for all times. Okay, so we can't... That would be nuts if we consider different K like per each time. So K is the total investment. Let us define this step. Let us define at this step the normalized weights. Define this. So that their sum at every time t equals to 1. Okay, so this means... yeah, that's why we have the K thing later, because we're normalizing over K. I get it. So this means the problem can be solved by finding the trajectory of t. So by analogy, the quantum mechanics we shall refer to the above costs. So rho is the Lagrange multiplier that imposes the constraint in equation 3. So let's look at these. Okay, so the constraint here is that the sum of all your investments will actually be k, right? Now, because we've normalized, this means that the sum must be 1. And this is where this minus 1 comes in. Now I understand this. So this is what we're saying here. Is we're saying that you have the constraint that, like, say, that's going to get complicated because I have to separate it into two levels again. So you have acid, like, how did I call this? So you have acid, no. So this is one acid, V0. Acid at time 0, and this is the same acid time 1. So you have 3 qubits. 3 qubits for this acid, right? No. This is, what am I doing? These are 3 acids, W00, right? So W00 is your acid. That's not like that's an acid. That's acid 0 at time 0. Okay. So what we want to do now is we want to basically, you know that because you have 3 acids, right? So this is acid 1 at time 0. This is acid 2 at time 0. The sum of these acids, like, it must be 1, right? Because we've normalized. Which basically means that, like, yeah, so we have these. Basically, minus 1 equals 0. So we have this constraint that we want to fulfill. And so the reason this is now, like, yeah, now the question is, like, how do you do that, right? And that's kind of, now I understand what I was reading yesterday about the Lagrange operators, is that that's a way to solve these. So yeah, we have our cost function that is kind of all these things here plus the transaction cost component, but we want to add this constraint. So Lagrange multiplier. So this is what we're saying is, what you have to do is you have to yeah, so what you're doing is so what I did is, like, this is gx, okay? So it's like it must equal 0. And so what then you have is you have the Lagrange of x and lambda being like f of x, that's the original cost function, minus these, which in our problem is rho, times these, right? So yeah, so that's Wt, so that's kind of like your, Vt, right? Like, that's what I call Vt minus 1. Now, why do we square these, though? Why is it squared? Oh, it's squared. Oh, it's squared for the same reason. It's squared for the same reason, like, we had it here. No, in the D wave. Oh, have I? Oh, yeah, that's the reason. So you square it because these. That's why. Yeah. That's why. Okay, that's cool. That's why you square it. That's easy then. Now I understand where this comes from. And ut, what is ut though? So u is transpose. So why u needs to be there? More compact. That's the constraint. More compact. Rho is a Lagrange multiplier that imposes the constraint in equation 3 as a penalty term. We have introduced the n-dimensional vector. We have introduced the n-dimensional vector u, n as in like the amount of it's an n-dimensional vector. Why? Which makes the constraint more compact. Why does it make it more compact? So it u sub n equals 1 for all n. So for all the assets is 1. It's just a way to ease the multiplication, I guess. Or to turn that into a sum. Kind of like the same what happened in here. Like the fact that you want to turn it into a sum of terms. And so now what you would have to go ahead and do is find this Lagrangian multiplier. So because basically what we're saying is the method can be summarized as follows: in order to find the maximum or minimum of a function with a constraint, you form the Lagrangian and find the stationary points of L considered as a function of x and the Lagrange multiplier. If the solution corresponds to the original constraint optimization, is always the saddle point of the Lagrangian function, which can be identified among the stationary points from the definiteness of the Borden-Hessian matrix. Or in other words, what we're saying is whatever minimizes the Lagrangian function is minimizing. So here we don't really care about like solving it. Like what we care about is that if we minimize the Lagrangian, it also means that we're minimizing the actual function. And so I think that's all you care. But you need to find a lambda or rho, and the way you do this is, oh my god, that's going to be complicated. That's going to be complicated. Because that's an easy example. Well, you built a system of equations, right? You built a system of equations. For the method of Lagrange multipliers, the constraint is. But you know what? Like, can Mathematica do these? I'm thinking to use Mathematica. Lagrangian multiplier Mathematica. I don't have to do this by hand. Like, there's got to be a way to find these things out. Or NumPy. Multipliers. Lagrange multipliers. There's got to be a way to find these with NumPy or something. Problem statement. Okay, so this is an example. So the circle constraint can be visualized like this. Code. They're doing it by hand. No, optimize. Oh, there's some fsolve and fsolve stuff. So you find the derivatives. Okay, so you actually find the derivatives of things, and then you find these and plotting the result. Okay, there's got to be a way to do that, so we'll figure it out. There's got to be a way to do that with NumPy, for sure. That's going to be next video. But I think we've broken it down. So I don't understand much the need for UT, but I think it's really just to get those I think it's really just to get those because what you're going to have with UT is like make it more compact. But why you're gonna make it more compact? So I'm here. So you're gonna have like your row, and then you're gonna have like we said we have 3 assets. Did I say 3 assets? I think so. Yeah, 3 assets times the assets, right? So the way this is gonna look like is you're gonna have like why? Okay. Yeah, that turns it into a sum. Okay. Yeah, so that's kind of like asset 0, 0, etc. So that like, these term times these plus the rest, and so that turns it into a sum. So you just have like basically that's what you have at the end of the day. Exactly. So this is this. Yeah, I mean, okay, that's squared and whatnot, but like, you know what I mean. Yeah. Okay. Why is it squared though? Again? It's squared because... Oh yeah, it's squared because of the -1. So it's squared because you won, or is it? Yeah, it's squared because you don't want the solution of not investing anywhere to be considered as a good one. So you must invest somewhere. So that's why you gotta square these to solve it. Okay. It's still a bit, it feels quite crazy. That's the only reason you square it, like, because you want to find the minimum. So you want to fine tune the equation to get there. So, okay, but I think we got a good grasp of the. Okay, so it took us 2 hours, literally 2 hours, to basically break down the Hamiltonian. So I understand roughly what it means. And here we have it. So this is the Hamiltonian. And so this is linear terms, right? And it's the expected return. Then we have the risk portion of it, which surprisingly, you can actually have some quadratic terms in there if I did this correctly, right? But the reason is because it's gonna have actually you're gonna have, like, it's about covariances, right? So you're actually gonna have, yeah, it makes sense in their quadratic terms. Of course, it makes sense in their quadratic terms. Like, come on. I mean, yeah, there's gonna be quadratic terms. Wait a second. Did I do this correctly? Did I do this correctly? I think I did this correctly. So these times these, like these times these plus these, and then these times these plus these. Yeah, that's more complicated. I have to recap how I multiply matrices. But essentially, you're gonna have all these multiplied by these, all the covariances. Something's off in here, but like, this is the covariances of all the elements with themselves, and so like, if you have these and these, right? The product is like these times these. Like, the product is actually it's just these things. It's like, because you do like the row times the column, right? So you do like these times these. It's more than that. Okay, these times these, etc. Okay, so I was a bit wrong, but yeah, that's, and then you do the same for these. And then you do the same for these. So yeah, this is going to add covariance. That makes sense. This is going to actually correlate terms. But what's interesting is that like when you've got like, you know, even when you have these, that's interesting. Even when you have these, there's correlation between the actual qubits, because this correlation, because those things like, you know, these each W00 is made out of like 3 qubits, and those need to correlate. And so those are quadratic terms. That's gonna be complicated. Then we understand why the phi's are squared. It's an approximation of the absolute function. We don't understand completely how or where lambda comes from, but we'll figure it out. And then we understand the last part. It's basically a way to add a constraint to the whole thing. So if f of x is the function that, you know, it's everything minus, like it's everything but the last term, then what you have in here is that part is in there basically because it's the constraint that you want to have, that the whole thing adds up to like k, now, or adds up to 1, right, because you're normalizing it. The reason you squared it is because you want the solution of all zeros not to be the valid one. So this is basically following the same example that is explained in here. That is yeah, I was so damn lucky. Like I was extremely lucky that I found these yesterday, like while I was just googling around. Um, yeah, because otherwise I have no idea. I would have never figured out where the -1 comes from. That's for sure, and where the square comes from either. So, and then you gotta find rho actually, and I don't know how we're gonna find these. I mean, at the end of the day, it's just a polynomial, so it shouldn't be complicated to find rho, I would say. But there's just too many variables, so I don't know how I'm going to compute these. Even just with this small, there's like 18 variables, man. There's 18 variables because it's 18 qubits. Maybe I should make a smaller example. Maybe I should make an example with 2 qubits, because otherwise I'm going to just kill myself. With 2 assets. 2 assets, 2 time steps. Yeah, probably I should do that. Anyway, I hope you enjoyed the video. It was heavy in math. It was a challenge for me as well. But I mean, that is so much more mature than what the Chicago quantum people are doing. Like, with all due respects, like I'm not, you know, the thing here is like you have like the qubits, like at the qubit level, you're really representing the K investment there. So you're really going there with the granularity of like saying I'm going to encode each investment, right? Each investment I'm going to encode with 3 qubits. So each investment is encoded with 3 qubits. Divided by K, of course. That's kind of why you're normalizing. That's key. Okay. Yeah, I'm really going to be intensely working on this in the next days. You know, doing the videos because I don't want to forget all these. That's something that I'll forget once I'm done with this project. But I'm happy that I understand. I think almost every detail of the actual Hamiltonian. So I'm really happy about this. Awesome. That was 2 hours video. Cool. Yeah, we're about the 2 hours mark. Hopefully the voice was recorded well. Yeah. Good. Stay tuned for more. And the next video is going to be getting this whole thing into actual code. I'll have to think how we're going to approach this because we'll probably reduce to 2 assets, but I'm not so sure how we're going to approach the construction of the matrix. I mean, at the end of the day, so how much qubits will we have with 2 assets, right? So with 2 assets, we will have. Okay, maybe I shouldn't. Maybe I should just use Q2. Like I should, you know, have a smaller Q as well. So I'll consider if I do like, say, 2 steps. Where is that? Like it's 2 steps times like 2 assets times. Yeah, if I use Q2, right? So Q2 then I just basically this is 8, right? So yeah, I'm gonna have 8 qubits. That's more manageable. That's more manageable. 8 qubits. That's a really small. That's a really small It's a really small amount of assets, to be honest. Gonna make a lot of a lot of investment. But maybe if I figure out a way to do this programmatically, then that wouldn't matter, you know? Maybe that's gonna help me. Like if I stick with the small example, it's gonna help me figure this out programmatically, and then we'll try to increase that. Ideally, use the asset data that I already got from Yahoo Finance. Anyway, I hope you're enjoying these. I'm having a lot of fun, and stay tuned for more. Yeah, definitely more coffee.